Welcome to section 2-5 from the 254, Determinants and Multiplicative Inverses of Matrices, day 2. If you haven't watched video 1, it might be a good idea to do it because we will draw upon base knowledge from day 1. In day 1, we learned how to find the determinant, and then from that we learned how to find the inverse of a matrix. Today we will be using the inverse of a matrix in order to solve systems of equations eventually. That's our end game. All right, so the goal is to solve systems of equations by using inverse matrices. One of my favorite applications of matrices. All right, so the identity matrix, it's like the number 1. Why is it like the number 1? Well, if I take the identity matrix and multiply it by another matrix, I get that matrix back. Well, that sounds confusing. Let's look at it just with numbers. This is why it's like the number 1. If I take 1 times 3, that just gives me 3. If I take 1 times 4, that just gives me 4. 1 times 5. That just gives me 5. Okay? That's how the number 1 works as a multiplier to a number. The identity matrix works in a similar way when multiplying a matrix. So the matrix I don't want to put that dot there. The matrix I times the matrix A just gives me A. And the matrix I times the matrix B just gives me B. And you probably guess it, I times C just gives me C. Now why is that? Well, it's because it is found by taking the original matrix and multiplying it by its multiplicative inverse. Huh? Well, check this out. The number 1 can be thought of as getting the multiplicative inverse of 3 times 3. That gives me 1. You're saying, hold on, hold the horses. What in the tarnation is that? Well, that's a negative exponent. The negative exponent of 1 tells us to take the reciprocal of the base. So 3 to the negative 1 is really like 1/3. So 1/3 times 3, that's 1. Similarly, 4 to the negative 1 times 4 is just going to give me 1, because this is 1/4 times 4. The multiplicative inverse of 4 times 4. And again, the multiplicative inverse of 5 times 5 gives me 1. So these are all multiplicative inverses. The same thing happens with matrices. I can get the identity matrix. That's the result of taking the multiplicative inverse of a matrix times itself, and that will give me the identity matrix. Again, so the inverse of B times B gives me the identity matrix for B. Multiplicative inverse of C times C gives me the identity matrix for C. Now the identity matrix can change. Okay? The way it always looks, the identity matrix, will always look like a 1 followed by zeros to the end of it, and then the next one starts with 0 followed by a 1 with zeros till the end of it, and that the 1s keep showing up on this diagonal. Okay? And that keeps going until I get to my bottom row, wherever that is, and that 1 will end with a 1. So this is going to look different, and the reason why it looks different is because it comes from the product of multiplying a multiplicative inverse of B times B, and B might be a different size than A, so it's going to be a little bit different. Now, I'm not going to test you on finding the identity matrix. but we will be using it. I don't want it to sound like it came out of nowhere. This identity matrix comes from somewhere, and we're going to use it, but we don't have to generate it all the time. Okay? So, let's think about that for a second. So where does this actually come into play? Why is this screen so messed up? There we go. All right. Where does this identity matrix come into play? And this is the powerful thing right now. Okay? If we think back to just good old linear equations, like this one, 3 times x equals 12. Oh, remember those days years ago when that was the toughest math problem you had to deal with? Yeah, Einstein was that way too, but then he got into some pretty heavy stuff. And he left that far behind. We're leaving it far behind, but we're revisiting it because the same concept comes into play. How would we solve this equation? We would do what? Divide by 3. Okay, great. For those of you listening in, this is a live recording brought to you from the 254. Okay, so I always wanted to do that. Yeah, we would divide both sides by 3, right? Divide by 3, divide by 3. But here's the thing, before you write that, dividing by something is the same as multiplying by its reciprocal. Right? You remember that? Instead of dividing by a fraction, you multiply by its reciprocal. Well, an integer is still a fraction, it's just over 1. So I'm going to multiply by its reciprocal. Okay? So I'm going to erase this, and I'm going to multiply by its reciprocal. But hold on. Instead of just multiplying by its reciprocal, I'm going to use exponent notation to write that reciprocal. So what I'm going to do now is this. We're going to say 3 to the negative 1 times 3x equals 3 to the negative 1 times 12. Because remember, 3 to the negative 1 is just 1/3. It's its reciprocal. It is also the multiplicative inverse because it undoes multiplication. So 3 to the negative 1 times 3 is just 1. So I get 1x equals 3 to the negative 1 times 12 is 4. Now 1 times anything is just that something. So 1 times x is just whatever x is. So x is equal to 4. Okay, so this is how it happens with just regular algebra numbers. Start with an equation. Instead of dividing by 3, we multiply by its multiplicative inverse. That's what undoes multiplying by 3. Okay? And that leaves me with 1 times x, but when we multiply 1 by anything, it doesn't change it. We do the same thing with matrices now. Okay? So if I had some known matrix A times an unknown matrix x, giving me a third matrix B. So I know, supposedly, I know what the values of A and B are, but I want to solve for what x is. This is what I'm going to do. Instead of dividing by a matrix, which we don't know how to do, we're going to multiply by its multiplicative inverse, which will undo the multiplication that's happening right here. So I can do A inverse times A times x. That'll be equal to, well, I got to do the same thing on the other side, A inverse times B. All right? Now, on the previous slide, we just got done saying that A inverse times A gave me my identity matrix. So now, A inverse times A defines as the identity matrix. Now here's the other cool thing. We just got done saying that the identity matrix times anything gives us that item back. So identity times A just gave me A. Identity times B gives me B. The identity times X just leaves me with x. So the unknown matrix can be found by taking the inverse of A times B. So this is all just the underpinnings for the real meat and potatoes of what we're doing. Okay? We do it with variables and unknowns because then they fit generic situations. Okay? We're going to solve this system using matrix operations. Okay, let me zoom in so this is easier to see. Get this out of the way. This is the system that we're going to solve using matrix equations and operations. We've done this one using elimination. We've done this one using substitution. We've done this one using graphing. But now we are going to use matrices. And it's a lot of work to solve this using matrices, but the same process can be used to solve 3 unknowns with 3 equations, or 5 unknowns with 5 equations, or 100 unknowns with 100 equations. And once we apply this to using computers and or graphing calculators, the only difference in the amount of work is how much time it takes you to type it in. You can solve it as fast as you can type it, which is pretty awesome if you're good with a calculator, which I don't like to brag, but yeah, I've been told that I'm pretty good. Yeah. Okay, so at least that's what my mom said. First thing we're going to do is we're going to set this system up as a matrix equation. All right, so I'm going to write this as 3x plus 2y. I'm going to chop this apart, and 2x minus 4y, put that in a matrix, is equal to 3, 2. All right? Now, this was one of our very first things we did with matrices. We said that this matrix says that this is equal to this, and this is equal to this, which is just what our original system said, right? It doesn't say any different. We're just writing it as a matrix. Now comes a little bit of a step here that might not be intuitive unless you're really math savvy, and that's to peel apart this matrix on the left into 2 matrices. It's like factoring a number. How we can factor 6 into 2 times 3. I can factor this as well. And I'm going to write it in. It's going to factor into what we call a coefficient matrix, which are just the coefficients of each term. And then the unknown matrix. And let me pause a moment before finishing this off and explaining how this works. Okay? If I was to remultiply this out, I would get 3 times x plus 2 times y. I should have used the color green because that corresponds to this first equation. And then I would get 2 times x plus negative 4 times y when I multiply it, which gives me my second expression. All right, so if I remultiply it out, I get back to where I started. And of course, I can't forget about the right-hand side, the 3, 2. All right. Now, think about this as a known matrix multiplied by an unknown matrix, giving me another known matrix. Oh, can you feel it? It's the calm before the storm of awesomeness. I just said awesomeness. I can't talk. I meant awesomeness. And that wasn't very awesome. Because this is what we said on the previous slide. I'm going to zoom way out. Boom. On the previous slide, we said a times x equals b can be written into an equivalent form, solved for x, the unknown matrix, as a inverse times b. So this can be thought of as x being equal to A inverse times B. So x and y can be found by taking the inverse of the 3, 2, 2, negative 4. So the inverse of that times what b is, the 3, 2. All right? And now let me pause for a moment for you to. So again, this is really going to pay off when we use a calculator, because we'll be able to jump from this one here, this one, to this one, put it in your calculator and have this system solved. But we need to do it by hand just a couple times so that we know where everything comes from and so that we don't think it's magic. I mean, I think my calculator is magic, but that's just personal opinion because it glows. No, it doesn't glow, but that'd be cool. So what we're going to do is now I need to find the inverse of this. I need to figure out what this is so I can do the multiplication. All right? So I'm going to figure that out right up here. The inverse of 3, 2, 2, negative 4 is equal to, whoops, the inverse of that, 1 over the determinant. Okay? So that's 3 times negative 4, negative 12 minus 4 is negative 16, multiplied by the switcheroo. I love that word. Negative 4, 3, those switch places, and these two become their opposites. Negative 2, negative 2. Now, if you don't remember how to do that, you can look back at the previous video, and I go over how to do that, or your course notes, and we talk about how to find the matrix in the inverse of a matrix in quite a lot of detail. So now I just need to multiply that out. So that gives me 1/4, and then 1/8, and then another 1/8, and then, ew, that one's an ugly one, negative 3/16. Okay? And that's just distributing the negative 1/16 to each element inside the matrix. Okay? So we've got that figured out. We figured out what the inverse was. And so now we can figure out what x and y are. All right? So this thing, whoops, wrong color. xy is now equal to 1/4, 1/8, 1/8, and negative 3/16 times 3, 2. Okay? Almost home free here, gang. Almost home free. I need to now multiply those two matrices, which we've done before in class. Okay? So I'm going to take and multiply those out. 1/4 times 3 is 3/4, plus 1/8 times 2 is a 4th. 1/8 times 3 is 3/8. And then negative 3/16 times 2 is a negative 3/8. I add those together, and I get 1 and 0. So my solution is 1, 0. That's the answer to the system. And you're probably thinking that wasn't any easier. It was actually harder than the other methods we've done. Yes, but this allows us to do systems with calculators, which will be much faster and more powerful. And we'll do that next time we talk.